finish up today. If you remember, the last time we spoke, we were talking about different design examples and going through the design process and the results that it can have. We got all the way up to, I believe, talking about the paperclip designs. And does that sound right? And we have one more design example to look at today in section 5.3, which is the robotic hand for a space shuttle. The space shuttle, of course, was the space program that started in the late 70s, early 80s, and went on all the way up until just a couple of years ago. Longest running space program in the history of space programs. And they did have this great big robotic arm on it, which was quite interesting. We're going to look at a little bit about, we're going to learn a little bit about this right now. So, this example starts on page 137 in the book, and it goes all the way through to the end of the chapter, page 142, so about 5 pages concerning this example. And they're going to go through the entire process here, starting with step 1, identifying the need, and defining the problem. So, the space shuttle. If you look here online, you see the space shuttle had this robotic arm, and it became quite famous for the many things that it did. They ended up having more than one at one point, I believe. It was often called, here they call it the Canadarm, because it was constructed, at least in part in Canada, and so they actually had Canada written right on it. You can see in some of these pictures. Not that one first, but let's see if we can zoom in here. Yeah, it says Canada right there. Canada. And it was an articulated robotic arm that could bend and twist and everything else. But it had quite an important function on the space shuttle. And that important function was mostly to move things, but also to move things, everything from moving satellites. For example, here you're seeing the space shuttle arm it looks as an animation here, removing the Hubble Space Telescope from the bay of the space shuttle, or it probably was pulling it into the bay of the space shuttle so that it could be repaired. But it also pulled it out. The space shuttle was big enough to hold the entire Hubble Space Telescope. But it also was used for, excuse me, moving astronauts around. Let me see if I can find a picture of that. There was a picture here somewhere. Here's one. So here's an astronaut standing on a platform on the end of the arm, and they were able to move the astronauts around the space shuttle and around the space station, so that the astronauts could do different things outside without having to spacewalk. Spacewalking is a bit dangerous, not a necessary thing all the time, because you're not tethered to anything. There's always the possibility of you kind of floating off into space and not being able to get back. It doesn't take much for that to happen. But the other thing that it was designed to do is to actually make repairs. So not just lifting and moving things, but it can actually do more fine type motor work. Placing things on, putting things together and placing equipment in the proper place, in the proper orientation and other things like this. So it was used as kind of an extra hand out there for the astronauts as they were working. I'm trying to find an example of that being used for that. It was also used for inspection. It had cameras on it, so it was used for inspecting the space shuttle. while it was in space and doing other tasks. Can't really see any of the other pictures that really show the other tasks in great detail. But the space arm was really quite important, and one of the things that they needed on it was some kind of device on the end of it that could grab onto things, because sometimes it was required that the arm would have to actually go out and grab onto a satellite or grab onto some other object out there floating around the Earth and bring it in for inspection or for repair or for whatever else. Here you can actually see a set of like little grabbing deals on there. It's not always visible. They had different things that they could put on the end of it. And in our particular problem that we're going to try to solve here, they're trying to create a hand, a kind of a gripping hand for the end of the spatial arm that can help them to assemble the International Space Station. Because the International Space Station is supposed to be this orbital platform up in space where they're just going to keep adding on to it more and more. They're constantly going to be building it, constantly fixing it, replacing things on it, adding things to it, and so on and so forth. And they needed a way to do that kind of work, because a lot of these things that they're going to put on the International Space Station are very massive, and even though you don't have any gravity up there that you have to worry about, mass is still a problem. You have to be able to accelerate the mass, and so you have to use something more massive, and the space shuttle is the best thing up there, more massive than the parts that they're putting on. So the first step, of course, in our process is to identify the need and define the problem. And so, of course, the engineering companies and the engineers themselves would have to go and meet with NASA and figure out what the problem is and try to make a definition that is very specific about what they need and what needs to be accomplished with this part. Excuse me. So let's put ourselves into the shoes of the engineer. We're now the engineer in charge of this project, and we're sitting down. We're going to sit down with some people to figure out what it is that we need to do for this robotic arm gripper hand thing. Who do you think we should invite to this meeting? Okay, so we're going to invite the team of engineers that we need, and that's for sure. We might have mechanical engineers, we might have electrical engineers and whatever else. So they're going to come along. But who do we invite to ask questions of? Who do we invite to? Go ahead. Okay, so astronauts, the people that are actually going to be using it or have used it before, right? It'd be a good idea to invite people who have used this robotic arm before. And it'd be a really good idea to invite the actual astronauts that are going to be going up with this thing to use it in the future after we build it, right? Because they're going to be able to give us some very specific things, information about what needs to be done, right? Who else might we invite to this meeting? Okay, that'd be a good idea, because we don't want to design something that can't be purchased. So we've got managers that we've invited to talk about money, maybe managers for NASA, maybe managers for different companies that are involved in the project, whatever. And we've invited the users, the actual astronauts. Who else, what other kinds of people do we need to invite to this? Okay, be more specific, what kind of technicians would play a role in this? Okay, so again, we might want to have some more people from NASA involved. That's true. Specifically, though, remember that we have people that are going to be using this thing, We have people that have already used this thing. And then there is the thing that we're using it on, right? So are there people that are involved with the parts that we're going to be manipulating that might need to be involved? The parts of the space station, for example. There might be, right? Whenever you're dealing with defining a problem, you need to think about everybody who might have something to say about this arm. So of course the operators, the users of the thing are going to have something to say about this. The people that are paying for it are going to have something to say about this. Of course engineers are going to have something to say about this. But also the people who are involved in the things that this is going to be used on. So they're not directly involved with the arm necessarily, but their parts or their space station is the thing that's going to be manipulated by this. So they're the ones that know, for example, what the materials of the space station are made of, how strong they are, how delicate they are, where you can grab onto it, where you cannot grab onto it. You can't just have people saying, well, that looks like a good place to hang on to, because many space-going vehicles have very thin, very fragile parts on them. They don't necessarily need to be super strong in space, because it doesn't take much to hold out the vacuum of space, quite honestly. And so you want to have them as light as possible so they can get up there, and that means sometimes things are pretty delicate. So we're going to have to have some people that know something about the space station, know something about what this thing is going to be used on, right? And this is a very easy thing to forget. It's very easy to forget who's going to be affected by this product, right? And they are important. On Earth, when we're doing a project and we're thinking about who's going to be affected, we usually do some kind of market research, where we're designing a vacuum cleaner, and so we take the vacuum cleaner out to the mall and we get a bunch of dirty carpets and we lay them out on the floor and we let people vacuum up with the vacuum cleaner, and we let them compare other vacuum cleaners with the vacuum cleaner we designed. And that's market research. We're now figuring out what the people who are going to use them and the people that are making the things or that own the things that they're going to use them, we're now figuring that out. We could also take it to the carpet manufacturers and say, hey, carpet manufacturers, what do you think is good in a vacuum, right? And we can start to define the problem that we're trying to solve, or define our project goals, we can think of them as. But we need to think not only about the users and the money and the engineers and the technicians, but also the people who are going to be affected by this product, or the materials or the parts or whatever devices that are going to be affected by this product. And then we need to get the people involved who can answer questions about that. Once we have talked to these people and we have gotten a lot of feedback from them, we're asking questions, we're learning things, and then we ask follow-up questions because of the things we've learned. Then we can move on to the next step, which is to create some kind of a problem statement, or just to kind of make this a little more clear. Let me see if I can get my thing working here. So it's working. And for this particular project, as the engineers talked to everybody that had an interest in this product, this is what they determined. This is what they were able to figure out. And they made this list from their notes from the meeting. So here is the list. This is the list of the properties that this robotic hand has to have, or they'd like to have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 properties. Each of these properties has a weighting factor between 1 and 10. 10 meaning it has to be this way. Anything less than 10 is just, we want it to be with varying degrees. For example, reliability is not absolutely necessary, but it is as close to absolutely necessary as possible. It's a 9, right? Whereas energy efficient is about 50% necessary. We'd like it to be energy efficient, But if it's not and it meets the other criteria really well, then we could accept that. Weighting factors. And then explanations. Why is it so essential? Soft grip is a weighting factor of 10. It must be a soft grip. Essential so that space station components are not crushed. Failure does not damage space station or shuttle. 10. Absolutely necessary. The failure of the robotic hand should not lead to other failures risking lives. Right? 9. Reliability. A failure could cause a mission to be scrubbed, which is very expensive, but it's not the end of the world. It's not going to kill anybody necessarily if it's not 100% reliable. We could live with 90+% reliable. Right? And so on. They've got all these different things, cost and time schedule and everything else. It's important to understand the details about your project even before you get started, and you do that by interviewing the interested parties or the affected parties. In fact, you can do that without even assembling all the engineers you need, because after you've done this, you may decide that you need a different set of engineers. You may decide that there's something that needs to be done and you didn't think about that. There might be some electrical components and you never even called an electrical engineer to the table. So these questions need to be asked, and they need to be asked in a very general way so that you can get all the information you can, and then get more and more specific as you learn more and more about the project to get ideas about the details that they want. So after you've got a list something like this that gives their priorities for their requirements and their priorities for those requirements, with some weighting factors and explanations, you can move on to assembling a design team that can meet these requirements, that have the expertise to design a product that will meet these requirements. And then you can identify constraints and criteria for success. Again, using the same list, you're going to decide how you're going to succeed. What is success going to look like when it comes to having a soft grip? Well, you might say, if it can pick up an empty soda can without crushing it, that is success. And you're going to write that down and say, that's one of the tests we're going to do. And we're going to design this so that we think it can do that, or whatever else. For each one of these things, you're going to have at least one or maybe multiple constraints and criteria for success. For example, mass might be that success is that it's going to be under 30 kilograms, right? And that'll be a good success, and maybe between 30 and 50 is marginal success, and maybe over 50 is failure, right? And some of these things you're going to create numbers that determine success. Some of them you're going to create a range that determines success. Some of them are going to be tests that you're going to do that are going to determine success. But you should have some kind of way to measure success when you're done before you even get started, so that you know what you're shooting for. Step 4, searching for solutions. Now that you know what the problem is, you've written down all the things that need to be done for this project, all the properties that this device needs, and you've got weighting factors and explanations, and you've created you've identified the constraints and the criteria that are going to determine whether or not you've actually created something with these properties. Then you're going to start the searching for solutions part. And this is where you go out onto the internet. You start looking at patents. You look at other kinds of applications. Maybe you're going to go to the construction industry and see what kind of mechanical hands they have on their devices. And maybe you're going to go to the paramedic industry and see what kind of things that they use to rescue people, or whatever else. Maybe you go to the robotics industry, go to a robotics research center, and figure out what kind of robotic arms are being used on robots and other things. Maybe you go to a car plant where they're assembling cars using robots and see how that's done. And maybe you go to the patent office and you look through patents of people that have patented ideas for this kind of thing. And there's all kinds of ways to do this. But you start doing research to figure out what kind of things have been done, what kind of things can be done, and to start the creative process for what you're going to actually do. And you collect materials, and you take notes, and you take pictures, and you go through things and whatever. and you collect all this information and you start to organize it. So maybe you have a bunch of different designs that are all based on the same kind of design, but they're all got a little different stuff. And you've got a bunch of information, you start to organize that all together in one place, and then another kind of, you start to separate things into files or into different boxes or whatever it is for whatever kind of information you gathered. You start to organize it so that you can find it easily when you need it again as you go through this design process. As you're doing that, you're going to learn some things. For example, here are two different designs that are existing designs for robotic hands. And they have something in common. You notice that each one of these has some kind of mechanical actuator, or maybe electromechanical actuator that moves or activates the hand. So this may be a piston, it may be an electromagnetic thing, it may be a motorized screw drive, whatever it is. Each one of these uses an actuator, and you might start to realize that you first need to figure out what kind of actuator you're going to use, or maybe you need to research actuators to figure out which one is going to give you the best possibility for a soft grip, or the best possibility for most reliability. Or, in other words, you have a moving part or some kind of part in here that needs to fit into these criteria for success. So, and then you also have the different kinds of hands. Here you have two separate moving hands. Here you have one stationary hand and one moving hand on the top. So you have to start doing research in who's done these before, what kind of results do they have, what kind of success do they have, did they go, and then go back and say, does that information help us to decide which one of these would meet these criteria the best? So you keep going back to here as you're going through this search for solutions step of the design process. You also may start figuring out designs. So this is beyond this class a little bit, but these are essentially schematics for different types of actuator designs, or different types of pistons, or similar things that can start this thing doing what it's supposed to do. It can activate the hand. And so you might have to evaluate, you might have to look at 2 or 3 of these side by side and say which one of these fits the criteria the best. Which one of these is going to be the most reliable? Which one is one of these going to cause damage if it fails? For example, you don't want an actuator that is going to open up if it fails. If it stops working, you want it to stay closed, because if it opens up when it fails, it might let go of whatever it's been moving, and that thing might drift off and hit the space station. So you want it to hold on to whatever it's doing if it fails. And those kinds of things have to be considered at every step of the way. And then, once you've started finding different options for the different parts of your design, different options for the hand mechanisms, different options for the actuator mechanisms in this case, maybe you're going to have a direct drive, maybe you're going to have a cable drive, whatever else, then you start to create what we call an evaluation matrix for each of the different designs. So on the left side, we have all the properties that are important to us. We have the soft grip, the failure does not cause damage, and so on and so forth. All these different properties with their weighting factors from the previous chart. And then here we're looking at 3 different options for this. We're looking at option A, option B, and option C. And this is just for the actuator. So that's what these diagrams over here. We have option A, option B, and option C for 3 different actuators. You don't have to understand these diagrams. But they've tested them, and they've started to evaluate how they would do, or how they do in tests that other people have done, or maybe that the engineers themselves have done. They test how well they do for these different properties. And you can see the first one tests at a 10, and then an 8 for the first 2. And you take the weighting factor and you multiply by the score that it gets in the test, and you get a weighted score of 10 or 180, which is 10 times 10 and 10 times 8. And then you go on to the next one, which gets a 10 and a 1. So 10 and a 100 and a 10. And the next one, which gets a 10 and a 10. So that's 100 and 100. And it becomes immediately obvious that some of these perform better than others. Even though looking at them without doing a matrix like this, it may not be obvious which one is best. But it becomes immediately obvious once you start doing this. You can see here that the scores get added up at the bottom, and the one with the highest score is going to be the best one. Even if it doesn't look the best, even if there are some parts about it that you didn't think worked as well as other parts, this one has the best score, and so you should really consider it. You definitely have to look at the things that have a weighting factor of 10. So the weighting factors of 10, that's really important. It's so important that you'd really like to see 2 10s there. And so this one does well in that regard. And then the next weighting factor, which is a weight of 9, those are also very important to look at. I would look at 10, 9s, and 8s. But the 9 is very important. I want to see how this one out here scored, and it scored a 10 on that. So I really like that as well. Okay. In fact, option C scored 10s all the way down, which is a really big indicator. But the point is not many things will score a 10 on every test and every evaluation you do. It's not really going to happen very often. But the point is that you explore the options not by just looking at them all at once. You look at specific things about them that are related to the properties that you're interested in. And maybe one of these has a property that we're not interested in. For example, maybe one of them is 10 times bigger than the other. But we never talked about compactability here. We never talked about how small it is. We don't talk about size. We talk about mass, but we don't talk about size. And so we can't consider that unless it becomes a problem, unless we decide it is important. So you have to use a very logical approach to deciding what design is best, or what product is best, or what component is going to be best in your design. And once you have done that, then you take a look at the one that scores the best. And you try to decide whether or not it's feasible. That's the next step, is a feasibility study. You choose the best solution, or best solutions if there are a couple that are close, and you try to decide if you can do it. Can we make this? Is it going to be too difficult to make? Is there an impossible thing about it that can't be done? Is it going to work in space very well? You start asking questions that maybe you didn't ask before, that were not necessarily parts of the requirements of the customer, but are requirements for the engineer. The engineer wants to be able to design this thing and actually be able to do it. And if they see something in there that they don't think can be designed, that they don't think can be done, the idea is good, the design, it looks good, but it can't be manufactured. Maybe there's not a material that can be as strong as they want it to be for this design. Or whatever else. You have to do a feasibility study. And at the end of that feasibility study, you have to go to the management and say, this is the one that we think is going to work best. Or maybe there's 2 or 3 that they think will work best, or whatever. So, now we're moving on to the end of the design process, which is to start designing the thing in more details. So up to this point, we might just have some very simple sketches like we had back here, but we maybe start to build a 3-dimensional model on a computer. And maybe we actually build a 3-dimensional model that can be not just a model, but can actually be a simulation. So we can make it work on the computer and see how it works, see how it comes together. And we can actually test it that way. And then we actually start to build it. We build a prototype and we start testing it. We start seeing where the faults are in our design, where we need to maybe go back and redesign and rebuild and retest. And we start looping back through and figuring this thing out. The iterations can go again and again and again. You can loop back through the design process many times as you need to do to get the design right, as long as you're not, running out of money, or your management says you're running out of time, or whatever else. Um, but once you've constructed it and tested it and done that over and over again until you have a product you like, then the design process is complete, and you should end up with a product that is satisfying the requirements of the customer, that is feasible to the engineering company, and that is ready because you have built it and tested it to be produced at that point. And that is the end of chapter 5. So far we have gone through chapters 1, 2, 3, and 5. We kind of just zipped through chapter 4 really quick. And for chapters 1 through 3 we had an exam, and now for chapter 5 we're going to have an exam. And I will be sending that out to you today so that you can complete it. And then we are ready to start our next project, the rubber band driven car project. The rubber band driven car project will be a project where I will give you, this is going to be more like a real engineering project where I'm going to submit myself to some questions from the students. I'm going to tell you the things that I want accomplished for this project. It will be partly my job to give you the information, but also partly your job to give me the information. We'll probably do that through email, where I will require each one of you to ask a certain number of questions to figure out what the requirements are for the project. And then you will go ahead and follow the design process that is outlined in chapter 5 the best that you can. Using the examples in chapter 5 would be a really good idea to follow them essentially step by step. But you are going to follow those. You're going to keep a record of what you do for each one of those steps in a journal of sorts, in a project journal. And then you are going to, at the end, present a car that meets those requirements. You will use the parts from your kit. You can use any parts that you want from that kit. You can even reuse parts. Maybe you reuse parts from your bridge if you want to. But at the end, your job is to present a journal showing me that you followed the design process that has been outlined in chapter 5 through several projects, and also the end product from that design process. Do you have any questions about what's going on the next couple of weeks here with this test and this project? Okay, so I will send out the exam, and then on Friday when we meet, I will give the instructions for the more detailed instructions for the next project, and also we will start the question asking process for searching for the first part of the design process. And that's all I have for you today. I'll see you later.